Okay, good. Thank you, Brooke. Okay, so we'll look at the whole concept of pH, and then looking at why we actually have acid soils before getting into what acid soils do to our crops and how we measure pH, and then the main thing in what do we do about it, which is in our case mostly liming. So let's start with just talking about what actually pH is. pH is a measure of the soil reaction. And so it usually goes from 0 to 14, with 7 being neutral and 1 being very acid or acidic, and 14 being very alkaline. And what it actually is that it's a measure of the concentration of the hydrogen ions that are in that solution where you measure the pH. Usually the hydrogen ions and the hydroxyl ions, they're usually bound into water, H2O, but there's always some free ones, and those free radicals, if you want, that's what we basically measure. And so when we say pH 7, we should really say pH -7, but nobody does that, so you just say pH 7, and it has that concentration of 10 to the power of -7, which is basically 1 unit in 10 million water molecules. So there's 1 free hydrogen cation in 10 million molecules of 10 million molecules of water. And also notice that when we change from one pH to another unit, that's a 10-fold change. So a pH 4 is 10 times more acidic than pH 5. So it's a 10-fold change there. Okay. So when we look at that pH scale, and we look at familiar substances, you can see that bleach would be very high on the pH scale, so very, very alkaline. Battery acid would be on the other end of the spectrum, so that's pH 1 or so. So that's a very acidic range. And like I said, 7 is neutral. One thing you notice on this slide is that natural rain is not neutral. So natural rain is actually under pH 6. So it's already in the acidic range. Our soils that we can grow something on, they range anywhere from just under 8, maybe 7.5, to maybe 4.5. There are some other soils in the world, but you can't really grow much on them. And so we have these various descriptions on basically how we describe particular pH ranges. And with a pH 6 or 5.6 to 6, we say it's a medium acidic. If it's 6.1 to 6.5, we say slightly acidic. And already 6.6 to 7.3, we'll talk about neutral. So we have these various descriptors, but basically once it's close to 5, it's very, very acidic, and it's very difficult to grow anything at that level. And the same, anything once it goes toward the upper 7, it's very difficult to grow anything there for different reasons. That might be a little bit small to read, but this shows the different essential nutrients that a plant needs. Most of them, not all of them, but most of them. Plus, it also shows some that are toxic to plants, like this aluminum. What you can see here, and then here this is the pH scale from 4 to 10. And the wider those bars, the more available that particular nutrient is. And that's why pH is so important. You can see that roughly in the slightly acidic to neutral range, that's where you have a lot of these important nutrients being fairly nicely available. Not overly available, but in a good range. While when we go into the acidic range, we have a lot of these nutrients really being not available at all, or in very small amounts, or in some cases in toxic amounts, which is in this situation where we see aluminum and also iron can be toxic at very, very low pHs because it's actually too much available. And we see the iron toxicity, we see that often in nurseries or in pots, in potted plants in general. So that's why pH is so important, because it makes nutrients available at certain ranges and it makes them unavailable or overly available at other ranges. So that's just kind of a general overview. So let's talk about why we actually have acid soils. And when you look at this world map, and you kind of look at, okay, where are the regions that are more alkaline, which is everything in blue, and where are the regions that are more acidic, you can pretty quickly say that wherever it's really dry, it's really alkaline. So you can see that here in Northern Africa, in the Sahel zone here. You can see that in the Mideast here. Also here in Turkey and into this region of Asia. You can see that in the United States and into Mexico here. Wherever it's drier, most of the time it's also more alkaline, and wherever it's wetter, like in the Pacific Northwest, here in the Southeast, in the Amazon rainforest, in the African rainforest, it's usually acidic. And so that points to rain being a major factor in all of this. And it sure is. And if you look at the US, it also becomes really clear. Everything that's brown, yellow, and green is basically more in the acidic range. Everything that's blue is in the more alkaline range. And you can see here, where is it brownest? Well, where it rains a lot. It rains a lot here in the Coast Range of Oregon, here in the Sierras, and certainly over here in the Southeast. So rainfall, high rainfall causes acidification. Why is that? Okay, well, there's a number of reasons for that. For one, as I said earlier, in the rain itself is somewhat acidic. So it's pH 5.6. And that is because we have carbon dioxide in the air. The carbon dioxide combines with the water and creates carbonic acid. And that's part of the rain that falls to Earth. We have also other contaminants like sulfuric acids, nitric acids. We don't have quite as much anymore as we used to have with the acid rain, because with the industrial pollution, that has been regulated in the Clean Air Act a little bit better. And so we'd have a little bit less acid rain as we used to have, but it's still in there. And so there's still sulfuric acid, nitric acid. And so that all makes the rain not being neutral, but being at a acidic range. And the other reason why we have the rainfall causing acidification is that the rain grabs, or the water that falls onto the soil or the irrigation, it basically leaches out some of these cations that are base forming. Bases are the opposite of acids. And so we have certain nutrients that are acid forming and other ones that are base forming. And water leaches out many of these base forming acids, base forming cations like calcium, magnesium, potassium, and sodium, out of the top soil and into deeper soil layers, or sometimes into the groundwater. And so just a reminder, cations are positively charged ions. And a lot of the nutrients that the plant picks up, they come in form of these ions. And there are some other reasons why we have acid soils, and I don't want to make this a chemistry lecture, but there's a number of transformation processes that basically also create acids in the soil. And then apparently plants pick up more cations, these positively base-forming ions, than anions. And so they usually get replaced with more hydrogen. And as I said earlier, number of free hydrogen ions in the soil is the pH. And so if you pump more hydrogen into the soil, because cations get picked up by the plant, then you also again have a somewhat acidifying effect on that, on the soil. And coming back to what kind of nutrients plants pick up, here are all of our essential nutrients that the plant needs to go through its regular growth cycle. And some of these are macronutrients and some of these are micronutrients. That basically just means these are picked up in large amounts. These are the micronutrients are picked up in smaller amounts. They're all essential, but they're just picked up in different amounts. But you can see that quite a few of these have these little plus signs, and that means that they are cations, and that's the form in which the plant picks them up. There are a few anions as well, like the boron, like the sulfates, like the chlorine. Those are picked up by the plants as negatively charged ions, but a lot of them are picked up as positively charged ions, which are cations. So the plant picks up a lot of these, and especially the ones that are picked up in large amounts, like some of the nitrogen, calcium, magnesium, potassium, those are picked up in huge amounts. And so these are some of the more natural causes of acidification. There are some agricultural practices as well that make the soil more acid. And the primary one is people using synthetic fertilizers. And so especially ammonium fertilizers, anything with ammonium in it has a very acidifying effect on the soil. Nitrates, not so much. Nitrates, they might convert into ammonium eventually. Ammonium converts into nitrates, but nitrates can also cycle back through some other steps. But in any case, if you use ammonium, you acidify the soil. And I just picked up these studies there from one of the extension publications. This shows here soil pH, higher pH here, lower pH down here, compares no nitrogen applied, and there's natural acidification. You can see that there's a downward trend, right? Just natural acidification because of all the reasons I just told you. But same soil, same site, nitrogen applied. See how the nitrogen, how the pH drops much, much faster. And this one, same deal here, but then different amounts of nitrogen applied. The more nitrogen you apply, especially in ammonium, then the faster it goes down. So there is a very clear connection between how much nitrogen you apply. It's actually about 0.1, a tenth of a unit for each 100 pounds of nitrogen per acre applied. So that gives you a rough sense for how fast the pH actually goes down with nitrogen fertilization. The other big one is when we remove residue, so like baling that hay or taking off the straw, we basically take nutrients off of that field, and a lot of them are cations. And so That's why nutrient removal or residue removal usually means cation removal, and it also facilitates acidification. Our grass seed farmers know that well, and they always make that choice. Should they basically take up the straw and sell it, but then have to fertilize a lot more, especially with potassium, or have more of a no-till system and leave the straw in place and maybe chop it up and leave it in the field and then fertilize less. So that's a choice that some commercial growers make. In some years it's better to sell it, some years it's better to leave it. But whenever you remove a lot of the residue, then you acidify the soil as well. And lastly, I want to mention irrigation. So irrigation means usually somewhat higher yield in at least in our region. And that means more fertilizers needed. So that's one reason. The second one is you irrigate, and with that irrigation, you leach these cations deeper into the soil. And so then they're not available and the topsoil acidifies. However, depending on where you get your water from, there are a lot of very calcium carbonate rich groundwater sources, especially here in the valley. So these cations that were leached out over the years, over the decades, over the centuries, they end up somewhere, and often they end up in the groundwater. And so when you have a deep well, you often bring up a very calcium-rich irrigation water, which can be actually problematic for a lot of our commercial growers, but for different reasons. But anyway, that can actually counteract the acidification. So with that, I want to break here and just see whether there are any questions about what pH is and what causes the soil to become acidic, either naturally or with agricultural practices. And you can chat them in or just...
I don't have a question, Stefan, but I was driving back from Salem today, and I noticed a number of agricultural farmers liming their fields.
This is the time. End of August is the time when you lime your field. And we'll talk more about liming, but liming, it takes a little while for the lime to actually have an effect. And so you want to do that early. And also now is the time where they have done their initial tillage passes. And now they put the lime on it, and then they will do an additional tillage pass and basically integrate that lime into the soil, because the more you connect that lime with the soil particles, the faster acting it will be. Instead of waiting for the rains to wash it into the soil, they basically do it now, and then with another tillage pass or with seedbed preparation, then they bring it into the soil and connect it with the soil particles. Any other questions?
I just had a comment to throw in.
Yeah.
We live south of Philomath, up in the foothills on Jory-type soils, one of these red hill soils that formed under coniferous forest. And when we first moved here, the pH was between 5.2 and 5.5. And our first year's garden was absolutely pathetic.
I imagine.
The only two things that grew well at all that year were the potatoes, which can tolerate a lower pH, and the green beans, which like to have iron as a nutrient, and everything else looked terrible. We limed that fall, and our gardens ever since have been much better. But yeah, we've seen what happens when you live in a rainy climate and your soil's formed under fir trees.
Yeah, I'll talk a little bit about soils, the different soils, and maybe, for example, in the Jory soil you mentioned, you wouldn't even try to get it up to close to 7, because it would be too much effort. But you can try to get it higher, so maybe it's to 6 or so, and then you can grow most most crops fairly well at pH 6. And if you integrate a lot of organic matter, that buffers some of that low pH in also. So I assume you do a lot of the best management practices, cover cropping, high residue crops, and so on. And then once you build up that organic matter, that buffers against that low pH a little bit. So a garden soil that has the same pH with a high organic matter versus one with a low organic matter will be much better able to grow crops, even though they have the same pH. Yeah. Okay. So let's move on then. Just a short note on measuring soil acidity. Obviously, if you have a real lab that can analyze it, great. It's the most accurate way of getting a good read on your soil pH. They basically take that soil, mix it with water, depends on the method, sometimes also with calcium chloride. And then they have a pH probe, and that pH probe was calibrated, and then they can look at your pH. So that's the most accurate. There are some field analysis tools that you can use. There are these color kits or probes or portable pH meters, and I show them here, where you can do your own soil water slurry and then mix it. Or you can take that soil water mixture and have certain reagents, and then they turn color. Or you have these test probes. These handheld meters can be fairly good if they're taken care of really well. And that is actually, but that is a little bit of a problem to always keep those really prepped and ready. The color test kits can be good if you always have fresh reagents, if you don't have them stored forever and then they become old. These test probes, they're not super accurate. I show you down here kind of the comparison between the different ones, and you can see that the portable meters and the color kits, if like I said, if they are up to date, and they can be quite accurate. The pH probe, not as much. But so there are some field analysis methods that you can use. One thing you should know about pH is that there is this concept of a threshold, and basically what it means is that plants, while you can, and I'll show you some of these tables. It says, okay, you have to have peas have to have this pH level, and garlic has to have this pH level, and this has, so that's okay, but know that plants have also a range, but that range is such that the plants do really well over a certain range, and then all of a sudden they drop off dramatically, and so it's a very rapid decline when you go beyond that threshold. So here you can see grass, for example, growing at 5.6, a really low pH, but our grasses can handle that here in the valley. But once you go just to 5.4 or 5.2 or 4.0, then all of a sudden they don't grow at all anymore. And so it's this threshold level. In this case, this is winter wheat. It grows well from 6.5, still grows well at 6, grows well even at 5.5, and then look what happened. All of a sudden it goes dramatically down in terms of yield. And that's very crop specific and even cultivar specific. And the reason why that is that, okay, we run into these deficiencies, and I showed you that slide earlier with the narrow bars and the wide bars. So that's one reason. There's also, once you get into acidic soils, the bacteria don't work as well anymore on that at all, and the fungi neither. So you don't have a lot of decomposition going on, and that means you have less nitrogen mineralization and availability for your crops. So that's the second reason. But the big one is the toxicity when you get into the real low ranges. So at 5.5, all of a sudden aluminum, which is a toxic element, becomes highly available. And then you have problems like this one. This is shows a young grain seedling at different pH with different amounts of aluminum in the soil, which is a function of the pH. And you can see here, basically at high aluminum levels, very low pH soils, the root growth basically stops. And then and here you see it in the range where it likes to be, and you have a lot of root growth. So that's the main reason why you have those are the main reasons, these three, why you have these problems in acidic soils. So what do we do about it? Well, we try to bring the pH up into a more neutral range, right? And we do that by adding lime. Lime is calcium carbonate, and so we're basically adding those cations that we all lost with the rain and with irrigation, and that was replaced by hydrogen with the ammonium fertilizers. We bring that back into the soil, basically. So in a way, you can think about an acid soil, and where these cations are basically attaching themselves to the soil, and the soil has negative charges, and it attracts positive charges, so the cations are positively charged. In acid soils, a lot of these negative, I call them docking stations here on the soil, are basically, there are, you have these cations on there, and a lot of them are the cations that we don't really want. So it's the aluminum, it's the hydrogen, and only every once in a while you might have some of these other cations. But once you add, basically you overwhelm the system with these calcium cations, and now most of these acid-forming cations get bumped off, and now you have the calcium sitting on that soil, and it neutralizes that soil. So that's sort of the principle of how liming works. However, there's a little bit more to that. And basically, when we talk about acid soils, you have two different types of acidities. You have an acidity, and that's a little bit hard to see with the colors, but there's these hydrogen ions that are basically in the soil water, in the soil solution. And in that soil solution, we have all these other nutrients floating, and that the soil solution brings those nutrients to the plant roots. But we have that acidity. That's what we measure with our soil, with our probe, right? That soil acidity. But then we have that acidity that's actually on the soil surfaces. And so we talk about the acidity that's measured with the pH. We talk about that active acidity. But then we have that acidity that sits on the soil itself. And we call that the potential or reserve acidity, or also exchangeable acidity. So there are multiple names for that other acidity, basically the acidity that sits on the soil itself. And so we basically, in liming, we're trying to neutralize both this acidity and this acidity. And so just knowing this acidity over here, so just measuring the regular pH is good to know, but it's not enough to tell us how much we should lime, because we want to basically replace this acidity and this acidity over here. And so that's the goal of liming: neutralize the active in the soil water or soil solution, and the one on the soil surfaces. And the soil has all of these negative charges on its surface, and the more it has, the more it resists that change of the pH with the liming. And we call that resistance to that change, we call that buffering. And that buffering depends on more or less on the surface area of the soil. The more little tiny particles we have in the soil, the more surface area it has, and the more it resists the change because it has more of these negative docking stations, basically. And so that's what we call the buffering, and that means that has implications to how much we need to lime. And different soils have different buffering capacity. And the amount of lime we need depends on that buffering capacity. So simply said, a sand has a low buffering capacity and a clay has a lot of buffering capacity. And so when we want to change a sand from pH 5 to 6.5, we need, and this is just for illustration purposes, we might need 1 ton of lime per acre, right? But if we want to do exactly the same on a clay, we need 4 tons of lime per acre. So we need 4 times as much to have the exact same effect because of that reserve acidity, because of that acidity on our soil, which has, the clay soil has a lot more surface area. So if you have a teaspoon of clay and you fold that teaspoon of clay, you fold those surfaces of that teaspoon of clay, you fold it into a 2-dimensional space, you would have the area of a football field. You know, if you would do the same with the sand, it might cover the area of the goal posts at the most, probably less. But just shows you the surface area of the soil, of a teaspoon of soil, is roughly a football field. So it has a lot of these negative docking stations on there on which these cations, these acidic cations can attach themselves to. So that's why we need a lot more lime in that clay compared to what we need in the sand. So the buffer capacity changes with the cation change capacity. Cation change capacity, you might have heard of that. It's called, it's abbreviated as CEC, and you see it on your soil test if you go for the full kind of full level soil test. And it basically is an expression of exactly the same what I just mentioned. Basically, if you have a lot of surface area, you have a lot of cation exchange capacity, you have a higher buffer capacity, meaning you need a lot of lime. That's all a function of surface area of the soil. And the surface area of the soil and the cation exchange capacity are a function of basically of these tiny little particles in the soil. And the smallest particles we have in the soil are the clay and the organic matter particles. More clay also means you have more organic matter. And basically, when you take a clay loam, it might have, a native clay loam might have a 5% organic matter, while a native sand might have only 1% of organic matter. And that has to do with how small the pores are in a clay soil. In a clay soil, the pores, the free area, the water and air filled area are so small that not even bacteria can crawl in there and decompose that clay. So the clay is protected in that clay. While in the sand, the pores are big, there's air, and the bacteria can basically go in there and decompose that organic matter. That's why a clay always has more organic matter than the sand does. But in any case, higher organic matter, higher clay means more buffer capacity, meaning in a soil that has a lot of clay, you need more lime. In a soil that has a lot of organic matter, and that's important for our gardeners, also needs more lime. If you want to change that pH. So the way we try to figure out how much lime we need is that we use this buffer method. And it's basically a carefully designed solution of chemicals where we know exactly what's in it and we know exactly what it does. And basically, when we have the soil that I had earlier here, we just overwhelm that soil and we replace it with that buffer. And then we basically, those hydrogen ions that were on that soil, we capture those. And then we measure how much of we have captured with a regular pH probe. And then we know how much was on that soil as a reserve acidity. So we basically knock them off, and then we can measure them with a regular pH measurement. And that's what we call the SMP buffer. This method will likely be replaced in Oregon because it uses some toxic chemicals, and they're working on a different one. And our soil extension specialist right now at OSU, she's working on that new method and trying to align the method so that a soil test that shows the will probably say Sikora buffer value, but it will still be a buffer value. So I don't know when it will exactly happen, but soon on the soil test, you will not see the SMP buffer anymore, but a different buffer. But usually, on a complete soil test, you have the soil pH, but it can be very different than the buffer pH. And the soil pH by itself will not tell you how much you need to lime. It's the SMP buffer that will tell you how much you need to lime. And then basically what the computer does in an automated soil analysis, or what you can do by hand, so to speak, you can go to a table, and then you can see, okay, this is my SMP buffer, and I want to have a particular pH. Maybe it's 6.0, maybe it's 6.4, depending on what crop I want to grow. And then I can read how many, in this case, it's tons per acre, but you convert that to pounds per 1,000 square feet or 100 square feet. And then you can see how much lime you need. Okay. So are there any questions right here? I mean, I covered a lot, but before we get into the gardening part of it, and what that all means for gardening, and I know I overwhelmed you a little bit with information, but can I explain anything better? Is there anything you want to look at again, or yeah?
So what is the bottom line for people like me who are not chemists and really don't understand a lot of this?
Okay.
When we get a report like this back, we're not looking at the soil pH value. We're supposed to look at the buffer value then? Is that what you're saying?
That's what I'm saying, because it reflects the soil type. Basically, if you have this pH value here, the SMP buffer for sandy soil would look very different than for clay soil. It will also look very different for a soil with a lot of organic matter, although the organic matter is not that there is some problems with that, because sometimes we try to get rid of the organic matter in when we sample the soil, but there's still a lot of integrated organic matter in the soil matrix itself. So it's reflected in here.
But the buffer value, that's still not what the bottom line is that then we have to go to a chart to find out what the actual pH is. And
no, you find out how much lime you need. What the actual pH is not that critical for how much lime you need. It will give you a rough sense, because if you have an extremely low pH like this one, 4.7, you basically know you can't grow anything on here. But it doesn't tell you how much lime you need to get to a particular pH range. You can only guess, and I'll get into that just right now. So let me, if nobody else has a question, I'm going to continue, and it will make more sense then. So the amount of lime you need depends on that, also on that target pH. So you might need, you know, a 5.5, you might need a 6, you might need a 6.5. But that target pH, basically 6.5 would be ideal. I showed you in the very beginning, I showed you a slide that said at the slightly acidic range, most of our important nutrients are available at the right range, at the perfect range. So they are available in the good range, not too much, not too little. And so 6.5 would be perfect. However, there is always a but. If you have a soil that's highly weathered, like Allen's Jory soil, to get that up to 6.5 would be, you would need a lot of lime and many, many years to get it up to 6.5. So you shouldn't shoot for that right away, maybe over time. But even that would be really, really hard. If you have a very highly weathered soil, like we have on the foothills of the Coast Range, or in the foothills of the Cascades. You know, drive by Willamette Vineyards on I-5 just before you get to the Enchanted Forest. You see that vineyard there, and it's really that red soil. That's all the Jory soil. Most Christmas tree soils are Jory soils. Many of our vineyard soils are Jory soils. And you don't want to shoot for 6.5 on those. You want to shoot maybe for 6, and that's okay. And for some acid-loving crops, I mean, blueberries, you would go even lower. You might go to 5 or so, or 5.2 or so. Or, you know, for very sensitive crops, and I'll show you a list later of what those are, you would try to go higher than that. So garlic, you want to be at least at 6.5. You know, that's a sensitive crop. Spinach, a little bit too. But so it depends a little bit of what your target is. So you know, in one of the extension publications, it gives you lime requirement for gardens in Western Oregon. And so basically look at your SMP buffer pH. And if that SMP buffer pH is, you know, between 5.5 and 6, you need 150, 250 pounds per 1,000 square feet, you know, or take a 0 off, 15 to 25 for 100 square feet. So that would be if you have that SMP buffer. But again, you need that SMP buffer value. And what do you do if it's not available? And Alan mentioned that right away to me, is that a lot of people come in with a particular soil, and we don't have a complete soil analysis. So we don't know what the SMP buffer is. Well, then you can only really, in all honesty, you can do a best guess or a somewhat of a guess. That best guess is based on a number of things. And so as a master gardener or in somebody who is in an advising role here, you need to collect information. And you need to collect information on, do you have any kind of pH value for that soil? So was there any analysis done with maybe with the pH strip, maybe with a color kit, maybe with something? If you have that, awesome, you know. If not, if you don't have that, you can make a best guess and say, well, how often have you applied lime in the last 5 years? If they have not applied lime in the last 5 years or even the last 10 years, you can pretty much be sure that here in Western Oregon, that pH is under 6. If they have never applied lime or not for a very long time. Very likely that pH has dropped under 6, which is problematic. So the other thing is that you can look at the soil type, you can look at soil management, and you can look at the crop that needs to be planted. And I want to talk about those just a little bit more. And as I said, you look at the time and amount of the last application. And so if soil information is really, really important. So you can go to the web soil survey and quickly type in the address of where that soil is being sampled, or that field that's in question, or that garden plot. And you can very quickly find what kind of texture that soil is if they don't know the texture. So in the wet soil survey, if you know how to navigate that, within a minute you can find that soil texture. So you will find, based on the address, you know whether it's a clay, a loam, whether it's a sandy loam, or whatever it is. So that's important. And obviously, if somebody comes in with the soil, which right now is not possible, but then you could texturize the soil if you know how to do that with the ribbon method. And then the other soil information that you need to collect would be get a feel for how much organic matter they have. If you have an old soil test, maybe they know whether it's in the low range, or in the normal range, or in the high range. That's good to know, because if you have a lot of organic matter, that kind of goes both ways. On one side, it protects against the low pH a little bit, but at the same time, if you want to change the pH, you need more lime. And you can also kind of get a feeling from your gardener by asking questions about what do they do. Are they applying a lot of compost? Are they doing a lot of cover crops? Do they do a lot of tillage? When they do a lot of tillage, it means they have very likely low organic matter. If they have a lot of compost and a lot of cover crops, it means that they probably have high organic matter. So you can get a feeling for whether they have low or high organic matter just simply on what they tell you about your practices. You can see here that if you want to change the pH by 1 unit, so it's from 5 to 6, for example, if you have soil that you find out maybe in the soil survey, hey, they are on a Newberg soil, or they are on a Jory soil, you can see what a difference it makes. For the Newberg soil, which is a lighter soil, and a loamier soil than the Jory, which is more of a clay soil, and all of these are more clay. You need half as much lime to bring that soil up to 1 unit. So if you are able to navigate quickly the soil survey, then you can very quickly find out whether they need a lot of lime or not so much lime. And then, okay, what crops do they grow? And I said earlier, in general, we want to be in that 6 to 6.5 range at a minimum. 6.5 ideal, but 6 to 6.5, we definitely want to be there. If a crop in here shows 6 to 6.5, it means it's a sensitive crop, an acid-sensitive crop. So asparagus acid sensitive, onions are, spinach are, garlic certainly is. And so you can get a sense here of what is a little bit more tolerant and what is less tolerant. Our orchards are a little bit more tolerant. Apples 5.6, filberts 5.6, peaches 5.6. So they're a little bit more tolerant. You don't need to constantly apply lime there, right? But then, like I said, some of those vegetables that a lot of our gardeners grow, they can be quite sensitive. And peas 6.0. With the legumes, peas and beans, I recommend always to apply a little bit of lime, because it helps with the nodulation. They can grow well in the 6.0, but you get a lot better nodulation. The nodules that fix the atmospheric nitrogen, you get a lot more of that if you have a higher pH. So actually 6.5 to 7 would be much better, because bacteria, those soil bacteria that fix the nitrogen, they love neutral range and not 6.0. So they would do a lot better, even though beans and peas can handle fairly well 6 and even slightly lower than that. Okay, so what does it all mean for somebody calling you up and say, hey, how much lime should I apply? So, you know, I would say, you know, I would tell them apply lime yearly, every year, on the lower range of things, or at least every second or third year. That's what I would tell them. I would tell them, well, you're somewhere, it should be, that application should be somewhere in the 5 to 15 pounds for 100 square feet, which is roughly how much also growers, you know, commercial growers would apply with their 1,500 to 6,000 pounds per acre. You know, on the high end, when you have a clay soil, when you have an acid sensitive soil, and if there have not been a lot of applications in the past. If you want to have an absolute, you know, and I hate to do that, but if you want to have one rule that applies to maybe many, but certainly not to everybody, a pound per square foot every year, probably right in Western Oregon. You know, but this is completely no idea what the soil is, no idea about anything. You probably don't do anything wrong with that, and you probably hold the pH somewhere in the okay range. But again, I'd rather have you ask a lot of these questions and then make a decision on whether you are on the low range or the high range. You should, if you are on the low pH, if you have a low pH, or very likely a low pH because you have never applied any lime, or because you have an acid sensitive crop, or you have a clay soil, if you need to apply a lot, don't make up for it by applying like 30 pounds per 100 square feet or 50 pounds. It's not good for the soil. You plug up all the pores and you do a lot of damage with that. So don't apply more than 25 pounds per 100 square feet. And gardeners are notorious for thinking a little bit more won't be bad. And it really is not good if you apply too much. Just for the whole soil structure, and then you can't garden in pure lime. So be careful and rather do it more frequent on a higher rate and bring it up slowly over time. And the other recommendation is always increase your organic matter because it buffers for that, for the lower pHs. That's always a good recommendation. So there are some of the resources I used also for some of the tables that you saw in this presentation, and I used some other materials obviously as well, but this is stuff that's easily accessible to for you. With that, we can go to questions. There's a bunch in the chat. I think I can answer those, or how do you want to proceed, Alan?
Well, I'll just read the ones from the chat to you.
Okay.
The first one is, how long does it take to bring pH up from, say, 5.5 to 6.5 by adding lime? I assume this is not an amount of lime, but how quickly it reacts.
Well, that's a question. Kim, can you clarify whether you mean how much or how or time?
Well, I think time.
Time. Yeah, definitely time.
Okay. So let's say you do have that amount of lime that you actually need, maybe based on the S&P buffer or maybe by feel. I hate to do that to you, but it's always that answer, right? That we always give. It depends, and it depends on the lime material that you use. It depends on meaning that there are different liming materials. And so ag lime is sort of the standard, but then there is burnt lime, there is hydrated lime, there's other limes. Dolomitic lime and ag lime are usually the standards, and that's for what most gardeners use, and that's what you can, that is available. So the type of lime. It depends also a little bit on how fine the lime is ground up. So a pelletized material that doesn't come apart very easily, maybe with water, so will take a longer time than something that's a very fine powder. So the finer the lime, the more finely ground the lime, the quicker it acts. Because it attaches itself more quicker to all of these soil surfaces, right? And then it can displace the hydrogen and the aluminum from these soil surfaces much more easily. So then there is another factor that has to do with moisture, but that's a whole different ballgame. But fineness and material, it can be within, I would just say, several months is sort of the standard, I would say. So if you apply it now, which is sort of a good time, once your garden is done, and then you could apply it now, and then it will by the spring or so, you probably have that pH change.
Great, thank you.
Okay.
We have a question, will the slides be available after the talk? And I can answer that one. Elizabeth is recording this session, and the Master Garden Association does have our own YouTube channel now, and so this will be posted there within a matter of a few days. Another question is, if a Willamette Valley garden is irrigated with hard well water, is it still likely to need lime?
Likely, yes. Yeah. Like I mentioned earlier, there's definitely a lot of calcium carbonate in that water, but it will not make up for the 35-40 inches of leaching rain that we're getting. And then in the irrigation itself, you add more water, and yes, I would say yes.
Okay.
It does substitute some compared to not so hard water, but it doesn't make up for what you lose.
Should you measure the pH of the well water that you used for watering your garden?
Should you measure the pH? Yes. If it's easy for you to do, it would. It will tell you something whether you can replace a little bit of that liming need with the water. There are other factors that go into that pH, but there's likely in a higher pH water, there's very likely more calcium in it, and it's good information to have, and it will guard a little bit against acid soils. Same kind of question as before that. Yeah, so it doesn't replace it completely.
Okay. And the last question that I see in the chat, are there other amendments that you would recommend being applied in the fall? Other amendments other than lime that would also benefit by fall addition?
A well-cured compost is fine to add in the fall. So that's because you don't, from a well-cured compost, you don't expect a whole lot of nitrogen benefit, which is, and so because that's already gone, the easily available, plant available nitrogen, the other nutrients will stick around. Anything that has really potassium and to a certain degree phosphorus, you can apply anything that has those elements in it to a larger degree. And that could be, even some slow acting organic amendments like bone meal and things, they can be applied not feather meal, not the ones that you need for nitrogen, like fish and feather meal and so on. Don't apply those. But everything that you use for calcium, potassium, even phosphorus, you can apply in the fall, and that will still be around. In the potassium will somewhat leach, but in the organic forms, they are nicely protected and they will stick around over the winter.
Well, there's been time for more questions to come in. Your emphasis has been on edibles. Should lime be applied to ornamental beds? And also kind of a related question, this person who asked that question right now only applies lime to their lawn, and someone else asks, what's the best time of year to apply lime to an established lawn?
Okay, so our lawns definitely need lime, and you can definitely see a well-limed, you can definitely distinguish a well-limed lawn from a non-well-limed lawn. I mean, grass is fairly tolerant.
This tone up is Quinn. It's down right now.
What's down?
Sorry, Stefan, I had it unmuted.
Okay, sorry. I wasn't sure whether I'm down or not. But anyway, lawn needs lime. Like I said, grass is very tolerant, can go down quite a bit, but every few years, you know, that I should definitely, you should definitely use some lime. What is the best time to apply it to existing lawn? Really, it doesn't really matter all that much. Not that critical. You can do it in the fall. You can do it in the spring. Don't do it late, when it doesn't rain anymore, or unless you have a lot of irrigation on the lawn. But it's not that critical, I would say, when you do it. It will kind of integrate into the soil matrix, and it will do its thing. No particular timing there.
And would it be a good idea to lime ornamental beds as well?
Well, just as you could make a list for every edible plant on what's the perfect pH. You could do exactly the same for ornamental plants. And I don't have a complete list, but certainly know that quite a few of the plants that we're using as an ornamental here in our area are quite tolerant to acid soils. So anything that's well adapted to the Western Oregon climate in general, which is the high rain winter and the no rain summer, if they're well adapted to this climate, most of these plants will be well adapted to acid soils. So your rhododendrons, anything in the Ericaceae family, all of those heather and so on, all of these plants, they do fabulously in very, very low pHs. But I'm sure there are some plants, especially plants that are not necessarily, that have to be kept alive with a lot of summer irrigation. So on all of those plants that don't do well in our Mediterranean climates, or climate that we have, I would basically go by that. And like I said, I don't have a complete list of ornamentals, but I would just go by whether they're adapted to here or not. And if they are, they don't need a lot of lime or hardly any. And if they are not, then they probably need some lime. That'd be my guideline.
Okay. Someone has asked if you would repeat what you should look for when you go looking for lime to buy.
So,
what sorts of things should you look for on a label?
Yeah. So most of the on the garden level, so not on the commercial crop level, most of the time you're given a choice between regular lime and dolomitic lime. Dolomitic lime has the added advantage of having magnesium in it, which is a nutrient that's used by a lot of plants in fairly high amounts. And so there's nothing wrong with using magnesium, dolomitic lime all the time, or at least alternate with regular lime. It might be a tiny bit more expensive, but it's not, to my knowledge, it's not significant. And it's perfectly fine to use always dolomitic lime. The ag lime, like I said, might be a little cheaper, has basically it's calcium carbonate, and does not have the magnesium. So the dolomitic lime guards a little bit against the magnesium deficiency. Sometimes you might be able to get other lime materials like burnt lime and hydrated lime. Those are materials that have a higher activity, meaning you need less of it. So anything that I said today about pounds or tons or anything, all related to ag or dolomitic lime. Ag and dolomitic lime are roughly the same in their, what we call the calcium carbonate equivalency. And so they're about the same, but other limes are different. Actually, let me just show you this one. Here's a slide. You can see the lime score. That's basically what I just talked about. The regular limestone or ag lime, calcium carbonate, and the dolomitic limestone have roughly 100%, and everything is measured on that 100%. And so there are some other lime sources that are more active, so we need less of it. And then there are some other ones listed here. You know, some people use wood ash. You know, certainly not as can have significant amount of calcium in it, but you would need a lot to really make up for that. Some people have access. Some of our growers take the paper mill lime down from the Harrisburg plant, and some of our gardeners might have access to that as well. That should be measured. It can be very, very effective. So basically, just like lime, regular lime, but it also can be not so effective. So that depends a little bit. But this gives you a little bit of sense of how efficient and effective the different materials are. Yeah.
I want to throw in a note of caution here. Hydrated lime and burnt lime particularly are usually things used in the construction trades for making mortar or concrete, and they actually can be quite caustic. Yeah. Whereas the carbonate-based limes that you would find in an egg supply or a garden store are going to be a lot safer to use. So my own recommendation is don't go for burnt lime. Let your concrete contractor use it and burn his hands up. You'll notice those guys wear rubber gloves a lot.
Right. Good point.
Someone has asked, do you recommend manure compost?
Yeah, it's a fine material. I mean, especially if it's well composted, meaning roughly, you know, having gone through the composting process that is basically mandatory for the organic certification. If it has gone through that full composting, manure compost is a good material. That one has usually a higher nitrogen content, and I would recommend adding that one in the spring and not in the fall. But that's perfectly fine, and you have depends a little bit also what manure. Be careful with a lot of people here in Benton County have access to horse manure and composted horse manure. Be very careful with that because there's very little manure and mostly shavings. And that can actually tie up a lot of nitrogen in your garden. I had that experience in one of my gardening classes where a few groups, student groups, forgot to apply the compost, and their crops did a lot better than everybody who applied the horse manure, compost from horse manure. And so be careful with that one, but most cattle or cow-based or chicken-based composts, manure compost are, you know, a good material.
Okay, I see a last question in the chat, and I will pose this as a last question. It's starting to get late. How does liming fit in with sowing a cover crop?
You can do that at the same time. Basically, when you kind of prepare your ground for cover cropping, you could apply the lime. That would, you know, that would be maybe a nice integration of multiple activities in the garden without having to do 2 times the soil preparation for that. So it fits perfectly fine. It doesn't do anything to the seed in terms of there's no negative effect. And the timing, most people, you know, if you go with the traditional cover crop planting of the fall, so obviously there's also the summer cover crop that bridges kind of over the summer, but most people do the cover cropping now, and seems like a perfect timing.
Okay, very good. Thank you very much, Stefan. Yeah. It's been a very informative talk. You've had lots of stuff in the talk, and a number of points you raised to the questions that were asked, and yeah, hopefully everyone now feels a lot more comfortable when we're back at the desk and getting soil samples in, of being able to make a good recommendation. Certainly not a simple question, but we do have some good guidelines that you've given us that'll help us make some better recommendations. Couple of general announcements for everybody. This talk will be available on the Benton County Master Gardener Association YouTube channel. The other thing I want to point out is that Elizabeth has been putting in a number of useful links for extra information that would be helpful. And I only found out recently that you can actually save the chat so that you can access these links later. If you open your chat window, and you can do that by clicking on the chat icon when you move your cursor to the bottom of the Zoom screen. If you look in the lower right-hand corner of the Zoom chat window, up comes a little thing that says Save Chat, and it will save the whole file on your computer in a folder called Zoom, and you can access it later and get to those links. So thanks everybody for coming. Stefan, thank you so much for your talk. Really appreciate that.
Very welcome. Thank you.